to show a selfie here of me and one of my goats. Now, it wasn't posed. I had the camera in my hand, and the goat came up and put his head on my shoulder. And, well, I'll turn off the lights for just a minute. He's a very nice goat, but he's big. He's about 80 kilograms. So, it's a chunk of goat. Anyways, on to more serious stuff. I made the link to the cleanest examples I have, even more explicit. Use the DAC and keypad examples shown on the dev board page. Those have all of the dependencies worked out for the big board with all the connections as done on the big board. So if we go there, we will find the construction stuff and then the board test example that I used to test your board initially, and a zip file that has the environment for the board. Then there's a DAC DDS sample code, an animation code for lab 3, and a keypad example for this lab. I'm trying to generate a keyboard expander or a I/O expander example, and I'm finding that it interacts badly with the DAC, so I'm working on that, but I don't have that yet. But the keypad example works fine. Has anybody had any problem with keypad? No. So, any questions about Lab 2 at this point? I got one question last night on Piazza about how many cycles are in this table, how many cycles of a sine wave are in this table. So it's 2 pi times I divided by the table size, and I goes up to the table size, so I divided by table size runs from 0 to 1, so the range of this table is from 0 to 2 pi, but after you do the multiply, and therefore it is 1 cycle of the sine wave. Any other questions on Lab 2? So let's start on Lab 3. You're going to do a video game. I showed you what the game looked like last time with a little video. And again, I put a link on here. There is a fixed point animation example on the dev board page, including forces for gravity and drag. And the video here is really boring, except that you can see that there's sideways now a ball bouncing as if it's a high drag environment. And if you let it run long enough, the ball will actually disappear off the bottom of the screen and go into Bit Never Never Land. So we need to talk about, to make this all go, we need to talk about the dynamics of how to calculate the balls that you're going to be animating. We have to talk about using fixed point arithmetic to speed up the result. And we need to talk quite a lot about direct memory access, since I'm asking you to make all sound effects with no interrupts. So the sound effects for the game have to be produced with minimal CPU overhead, which means no interrupts. No code running to actually transfer the samples. And the game controller there's going to be a potentiometer, also known as a trim pot. There's a picture of the potentiometer. And you're going to have a screwdriver, or inevitably somebody uses their little fingernail to turn that thing. But screwdrivers are easier. And that will control the position of the paddle on the screen. So for the screen, the paddle will move up and down, and its position from 0 to 240 will be controlled by the potentiometer. So we have a few things to talk about here. I'm specifying that the frame rate has to be faster than 15 frames per second. That is about the lower limit where people will integrate a set of still images into motion. I don't think Saturday morning cartoons are a thing anymore. But when my kids were growing up 20 years ago, they got up every Saturday morning and watched some ridiculous set of animation. And the television runs at 30 frames per second, but the animation, to save money, was only updated every other frame, and so the animation ran at 15 frames a second. And yeah, it looks a little jerky and a little cheesy, but you still see motion. So I'm asking you to stay above 15 frames per second, but to animate as many balls as you can at 15 frames a second. The dynamics are going to be hardball dynamics. So if you have two balls that are approaching each other, if this is ball I and this is ball J, then this is Rij. It's the difference between the two, it's a vector. And let's say that we have approach velocities that look like this. So this would be Vi and this would be Vj. Then we need to know where these balls are going to go after the collision between them, and they're going to come together and they're going to bounce off and go up there. But we want to explicitly represent the motion of the balls before and after the collision. So the question is, where should we start on this? There's several threads. There's a dynamics thread. There's a fixed point thread, which is really related to the dynamics. There's DMA. I think I'm going to start with the dynamics. And do you all have an image of this from last time? The balls firing around. So this is a fairly small version of the same dynamics. And you can see that balls are bouncing off of one another and banging around here. And there's some errors in it. As long as the errors are small, I don't mind. You notice I made it slightly easier than in this image, because in this image the reflections were off of a hemisphere. So calculating the normal was harder than off of a flat paddle. So then what we're going to do is we're going to so Rij, or Ri, is some x times x hat being the unit vector in the x direction, plus y times y hat, where y hat is the vector in the y direction, unit vector in the y direction. So we're going to do the analysis, we're going to need Rij, the distance between the balls. when Rij, when the magnitude of Rij is greater than the ball radius times 2, when Rij, the magnitude of Rij is greater than the ball radius times 2, there's no forces on the balls at all. When the balls hit, they bounce instantaneously. Okay. So we're going to need Rij to tell when an impact occurs. So this is going to be Ri minus Rj. We're going to need the velocity of each, we're going to need the approach velocity, Vij, which is going to be Vi minus Vj. And this is the usual definition of vector subtraction, right? And then the way we're going to figure out where things are going to go, so let me try and draw a slightly accurate version of this. We have some Rij, this is ball I, this is ball J. Let's say we have a Vij that looks like this. What we're going to do, now the balls are frictionless. That means that they can't, there's no spin. If a ball hits at an angle, the only velocity that changes is in the direction of Rij. Perpendicular to the direction of Rij, there can't be any change in speed, any change in velocity, because there's no friction. So there's no way to get a force in this direction. There can only be a force along this line. So what we're going to do is we're going to project this vector, we're going to project Vij onto Rij. Then we are going to negate it, bink. And that's the velocity vector, that's the change in velocity after the impact. And then we're going to take that vector and resolve it back into xy. So there's 3 steps. Project Vij onto R to get the component of the velocity that will change due to the impact. We'll negate it to get the actual change in velocity during the impact. And then we'll project it back into xy so that we can plot it. You probably all remember how to project a vector, one vector onto another. And that is we're going to take Rij and dot it. That's the dot operator, not multiply, not scalar multiply. It's dot operator times Vij. And because R has a non-unit magnitude, we have to then divide that by the magnitude of Rij to normalize back to the correct length here. So that's the projection. That's the projection of Vij onto Rij. Then we're just going to negate that. Vij over the magnitude of Rij. And so now that's this step. And then we need to project it back into xy coordinates. And to do that, we can recognize that Rij over the magnitude of Rij is really a unit vector in the direction cosine theta x plus sine theta y hat. In other words, it is exactly what we need to multiply by to project the the new velocity vector back into xy. So then delta V for ball I, delta V for ball I is equal to minus Rij over the magnitude of Rij times the dot product of Rij times Vij over the magnitude of Rij. Oh, good, the magnitude appears twice. That means we don't have to take a square root, because we could just calculate Rij, the magnitude of Rij quantity squared. That is what you're going to be calculating for each pair of balls. Now, there's a bunch of simplifications you can do. One is, until there's a collision, there's no force. When there is a collision, then we know what the magnitude of Rij is. At collision, the magnitude of Rij has to be equal times 2 times the ball radius squared. So if we choose the ball radius carefully, let's say we let the ball radius equal 2. 2 times 2 is 4 squared is 16. We can replace this divide, a slow, inefficient operation, with a shift right 4 bits. So this implies that 1 over Rij magnitude, if the ball radius is squared is equal to 2, is equivalent to a shift right by 4 bits. So one of the questions in the homework is, take this vector code, convert it to a scalar C code. Because there's no vector operators in C, sadly. There's only scalar operators. So you need to convert this nice compact vector equation into a mess of equations for doing the dot product in scalar terms. Now, once you've got the delta VI, there's a bunch of stuff you have to do. And it's messy enough that I decided to give you a little bit of pseudocode on this. And so the pseudocode might be for each ball from 1 to n, then for each j from ball I plus 1 to n, compute the approximate Rij by checking if both delta x and delta y are both less than 4. If either one of them is greater than 4, if either delta x or delta y, the difference in coordinate between the two balls is greater than 4, there can't possibly be a collision on that step. And then we're going to compute the exact radius. Why do you think I broke that? Well, that's a really obscure question. This turned out to be a bug a couple of years ago that took the students and me a long time to figure out. And the reason is that we're going to have to check that x and y are both less than 4, because we're going to be using fixed point arithmetic. And we're going to be using a fixed point arithmetic that has a range of plus minus 32,767. You say, well, nothing on the screen can ever be that far apart, but it can if you square it. In fact, any difference in coordinates of greater than 181, I think, 181, results in an overflow which will imply in your code a false impact. So, you have to do this general range check first. Make sure that delta x and delta y are both less than 4. And you should do that because it's fast to do that calculation. And almost every pair of balls is going to fail that test, and you can throw them away and you don't have to do the rest of the calculation on them. Right? You don't have to do the calculation. Then, if it doesn't pass that test, then you have to do the details. Then you have to say, all right, I'm going to get the magnitude of Rij exactly and see if it's less than ball radius times 2. I'm not taking the square root again. I'm squaring this value so I can use squares and avoid square roots, because square roots are very slow. And there's a technical detail about a hit counter I'll talk about in a minute. Then we're going to compute Vij delta Vi and add Vi to delta Vi to Vi and subtract delta Vi from Vj, because we are assuming equal mass for all the balls. We have to conserve momentum. This step conserves momentum right here. And there's an approximation here, and the approximation is that we're stepping these balls at uniform time steps. So sometimes the time step will take it to the point where the balls overlap or even go through each other. And so the sign, the SIGN of Rij is incorrect, and you'll get some weird artifacts because of this. And the main weird artifact is that balls will start to orbit each other. They'll become a bound state like a molecule, which is kind of cool, but not what we want. And so we're going to fake it. And the way we're going to fake it is we're going to say, if a hit occurs once, we don't let it occur for n time steps. That allows the balls to get away from each other so they can't stay bound. So if there is an impact, then we're going to set the hit counter big enough to avoid particle capture. We're big enough you're going to have to play with. It should be not too big, but it'll have to be some. It might be 4 steps, might be 10 steps, depending on how you do it. So the hit counter is going to inhibit further interaction of that particle with any other particle for n time steps. Once you've done that for all the particles, you've added up all the velocity changes for each particle. And there's some coding hints here that you're going to want to run through. But then the next step is going to be to take the new, after you apply delta V, then we're going to, you need to you're going to have to simulate friction not between the balls, but between the balls and the table. We're assuming that there is these are like billiard balls on a table, and the table is a little bit sticky, and so it slows the balls down. And one reason for doing that is it helps the numerical stability. If there's no losses in a system, and you have a little bit of numerical inaccuracy, that can mean that you actually add energy to the system and everything speeds up. Adding a little bit of drag ensures that you lose energy on every step, and stuff comes to a halt sooner or later. So we're going to add a little bit of drag in the sense that you're going to take the new x and subtract off a small amount of it with some drag coefficient both in x and in y, and then do a integration of Vx times dt plus x to get the new x, the x at the next time step. And this isn't a wonderfully accurate method of integration. It's called Euler integration. It is easy. It is not accurate, but it's easy. Then you have to make sure that if you've hit a wall, you have to handle that condition because you don't want the balls to fly out through a wall. So if you hit a horizontal wall, you want to reflect the vertical component of the velocity, negate the vertical component. If you hit a vertical wall, you want to negate the vertical component of the velocity. And then lastly, you're going to have to delete any balls which are collected or which make it past the collector or make it past the paddle. The paddle. So balls that go off here disappear. Balls that get collected disappear. You're going to have to then recycle those to the side of the screen so that you can reanimate them from the right-hand side of the screen. So there's a lot of sort of dynamics that has to be done, and that's why I'm giving you 3 weeks for this lab. There's a lot of details that you have to deal with. It's a little bit longer lab. Also, fall break is in the middle of it. I would say, though, that after the first lab, at the end of the first lab, a reasonable checkpoint is at the end of the first lab, you can bounce balls off of each other. Yes?
When you say lab 3 checkpoint on week 2, does that mean that we're going to have like a formal checkpoint with TAs? What does that mean?
I am not going to enforce it this year. Next year I am. This year I'm going to say, if you don't, it would be a really good idea to have bouncing going at the first lab. Because after all, you're going to lose a whole weekend here, right? Fall break. You're going to lose 4 days. You're going to lose a Monday and a Tuesday, as well as the weekend. But there's not going to be a formal checkoff. I did that in 5760 last semester, and it helped people organize their time. I just forgot to start doing it this semester, but next year I won't forget. I think. So now there's a set the time. Let's see, faster than 15 per second. Oh yes, this is an interesting website that shows you what different rates look like. Let's go to 5 frames per second. Eek. Let's go to 10 frames per second. That's starting to look like animation. If we go to 15 frames a second, that's not bad. That's where we're going to ask you to be, at 15 frames a second. But there's a further problem, and that is a typical way to do this would be to have a thread execute every 67 milliseconds, right? 15 frames a second is 67 milliseconds. But threads are not, since this is not a preemptive system, the thread time, the wait time, is merely a lower limit. You can guarantee that the thread will wait at least that long before it executes again. And in the case of this lab, you're going to have a varying number of calculations depending on how many balls are actually on the screen. If the user manages to capture a bunch and get rid of them, then you don't want the game to speed up. You want to stay at 15 frames a second. And so you have to make a loop which always takes the same amount of time in the presence of a variable amount of calculation. And there are various ways of doing this, including having another interrupt. But what worked well last year was a little simpler. And that is you fall into this compute loop, you do a PT get time. Remember PT get time? Get time returns the time in milliseconds for you from a precision interrupt driven counter. So you don't have to invent your own time base for lab 2 either. You can use PT get time to tick milliseconds for you. Then you're going to do the calculation with however many balls happen to be on the screen. So that's the pseudocode from before copied back in. And then inject any new balls into the playing field, if any. Check for user interaction by reading the ADC and buttons, if any. And then do a yield time of 67 minus PT get time minus the begin time. In other words, you're only going to wait for a time which is the leftover of 67 milliseconds after you've done all of the calculation. What do you think happens if that goes negative? This argument goes negative. Well, I'll tell you what I think happens, and that is that the timer that's involved in this is an unsigned long, and so you're going to get a wait time, a yield time that is about 2 billion milliseconds. And that's like 3 months. So the system is going to effectively go dead. It's just going to stop. So you may want to do a range check before you actually make this call. You might want to do a range check to make sure this is actually a positive number or 0. Actually, if it's 0, you just fall through, you don't yield, right? Or you yield, but you don't wait. So you're going to do the dynamics. The dynamics is going to change speed with the number of it's going to take longer or shorter amount of time depending on how many balls you're actually calculating. And this time construct, this yield construct, will allow you to keep a constant frame rate of about 15 frames a second. So clearly a strategy would be start with a few balls for testing. Start with 2. 1 red, 1 green. So that when they bounce, you can tell which direction they're going. If they pass through each other, that's an error. They ought to go boring and bounce off. Then fire them at an angle, so they fire off at an angle. Make sure the various cases work with 2 balls. Then once you get the dynamics running, once you get the dynamics calculation running, go to 10 or 20 or 30 balls, and then see how many milliseconds you have left over and start increasing the number of balls. You'll be limited by a couple of different things. One is you may run out of memory because each ball position is going to take a certain amount of memory. It's going to take some state memory. It has to have an X and a Y and a VX and a VY for each ball. So there's 4 state variables for each ball. Or you may run out of time, depending on exactly how many structures you get animated. So yes?
So you said, when you say run out of time, is that the time when there is no yield time in that proto thread? And like the proto thread would be called again on top of itself?
Well, it will never, because it's a non-preemptive system, it'll never actually do that. But instead what will happen is your frame rate will go down. So the system will start to bog down and run slower when you run out of cycles in that compute loop. So efficiency is going to be important.
kind of self-correct if like it's just on the border and say you got rid of a ball in the video game where you wouldn't even notice it, or would it like actually keep bogging down?
So either one could happen depending on how you did the logic. You could say if I'm going over less than 15 frames per second, delete a couple of balls.
Okay, just make how many balls show up slow down.
You could do that also. You could have the ball creation rate slow down. You could just do worst case and say that if every ball is on the screen moving, I can still make the deadline. And the strategy you choose is going to depend partly on how much stamina you have in making it all work, because it's fairly complicated. Any questions on the dynamics? There's vector arithmetic. Oh my gosh. How long has it been since you did that in a computer science class? So, but I'm going to ask you to, again, to convert this to scalar code, of course, which you have to do to program it. And but let me say also, at various points in the description, you will find that it says start firing balls of radius 2 pixels on to the right hand edge of the screen with pixels per frame of -1 to -3 and something like 1.5 to -1.5 pixels per frame. The speed distribution in the y direction must be uniform and random. The x values can be fixed between values indicated. You can vary this to make the game more playable if necessary. In other words, these are recommendations. They are not hard requirements. As long as you meet the general requirements, you can mess with the numerical values of the parameters to make it more playable. You can make the paddle a little wider. You can make the catching areas a little wider, a little narrower. As long as it's playable in a way that you like and meets the overall general specs of the lab. Draw a paddle consisting of a line segment with a size about 5 times the size of the balls. You can vary this to make the game more playable or to produce harder levels of play. Again, it's variable. You'd be graded on the number of simultaneous balls you can animate, and you must animate at least 30 balls. That suggests that it's a good idea to have a ball counter on the screen. That's relatively accurate. Any questions about this? Now the other aspect of this. Now let me talk just a little bit about DMA before the end of the lecture here. So direct memory access is essentially a coprocessor that runs on the chip. There are 5 DMA channels. There's 5 DMA channels that are completely separate from the CPU. These are not part of the CPU. They're completely separate hardware. Each one of them can be a bus master. It can issue memory addresses, just like the CPU. So each one of these DMA channels is a bus master that can ask for data from memory or send data to memory. Each of the channels is programmable as if it were a CPU, except that instead of writing opcodes, you set up registers which give global operations. You set up counters, you set up sizes, you set up vectors, you set up pointers in the DMA controller, and then the DMA executes an endless loop, a potentially endless loop of memory moves. Because all of the peripherals, the analog to digital converter, the SPI port, all of the peripherals are memory mapped, the DMA can send data to or from any peripheral at about 3 million per second, faster than the CPU can. So you have this weird situation then of a completely, truly parallel processor doing something for you if you can only aim it in the right direction. One of the, I don't think you're going to do this in this lab, but one of the things that I've done with it is to grab data from the analog to digital converter at a megahertz. In fact, it's the only way to get data out of the A to D converter at a megahertz, and barf it into main memory, into data memory. In your case, what you're going to be doing is taking a table of 1 or 2 cycles of a sine wave and copying it to the serial peripheral interface port over and over again to make a tone burst. That entire copy process of all of the sine wave samples and the repeat over and over again for, say, half a second will all be handled with 0 CPU cycles. You set up the transfer, you stand back, and let the data flow past you. So you're going to configure a channel. Once this channel is configured, it can do data looping. It can send data in a loop. It can send data for a certain amount of time. It can even terminate a transfer on a given value of data. In other words, it can do a conditional termination. So you can move data. You could do a conditional. Do you think it's a Turing machine? Anybody CS-y, kind of CS-y kind of people here? Do you think it's a Turing machine? Do you think it's compute universal? I think it is, but I can't prove it right now. So this is by way of warming up your brain for this. There's quite a lot of detail that we have to go through, and I will go through. But there are at least 5 bus masters. There's the CPU, 4 DMA channels. I believe that the hardware USB controller is a bus master. And then there are bus targets, which include flash memory, data flash, and peripheral memory. And each one of those can be accessed at the same cycle. So you can, for instance, read a peripheral, write it to data RAM while executing code out of flash, and that can all happen on the same memory cycle. So this is truly parallel, truly concurrent. I would say for the audio synthesis we're requiring that eliminating an interrupt service routine to do the audio is going to save you about 10 to 20% of the CPU time. And therefore you'll be able to do 10 to 20% more balls, animation-wise. So the two big chunks of this are the dynamics an animation of the balls, and direct memory access control of the sound. I'll give you a lot more information on that. I have a bunch of examples on that. There's another small detail, and that is that serial peripheral interface has to be set up in a very certain way called framed SPI. And I have some examples on how to do that also. So you're going to have to get down into the lower level stuff just a little bit to make this go. So any questions about this right now? You all got the message about the new due dates, right? Piazza. I sent out another message today reminding people that there are some perhaps cleaner examples on the dev board page. And as soon as I can get a port expander working the way I like it, I'll put that up. We have 5 minutes, so let's see. The last lab of lab 3, so that's about 4 weeks from now, you have to have a good idea what you're going to do for a final project. You have to be able to give us a 2-page summary of it. So it's not too soon to start thinking. And again, try and relate this to something you actually care about outside of class, perhaps. What do you do outside of class? Besides working on other classes, of course. Ah, that's what you want, a robot to do some homework. That's, yeah. So start thinking in that direction. There's various ways of getting inspiration on this. One possibility is to go to some of the sites like Adafruit or SparkFun, commercial sites, and see what they're doing, because they have all kinds of cool projects up there. Hackaday.com has a phenomenal number of projects. Something like 60,000 projects online. See what people do. So come up with questions on Lab 3, and I'll see you Monday. Except for, I'll also be in lab course this afternoon.